Okay, let's talk about some of the pressures here. So we're going to look at the events again, but from a different perspective, now looking at how the pressures are changing. So phase one, atrial pressure is starting off low, but then it's going to slowly rise towards the end as the atria begins to contract to get that last flow of blood out into the ventricle. So there's a small rise in both atrial and ventricular pressure towards the end of phase one. In phase two, we're going to see all four valves are closed, rapid rise in ventricular pressure. This is the isovolumetric ventricular contraction, and the atrial pressure will fall, as we can see in the curve, but ventricular pressure will be rapidly rising, okay, as you prepare for ejection. Phase three is ejection. Ventricular pressure is going to rise at first, but then drop as blood leaves the ventricle. Atrial pressure will continue to fall until the end of systole, and then it's going to remain the same and slightly increase towards the end of systole. So it's going to sort of stay stable because the ventricles are contracting, AV valves are closed in phase three. And then thinking about what happens with the aortic pressure specifically. So now we're focusing on just the left side of the heart and just the aorta, which is the exiting artery from the left ventricle. So we're going to see that the aortic valve closes during diastole because the heart is filling, and so the semilunar valves should be closed. The AV valves are what should be open in diastole. So blood is going to be leaving the aorta, but the pressure is going to be falling. So pressure falls as blood moves away from the aortic valve and out towards the systemic vasculature. And so we're going to see the lowest point in diastole being recorded as the drop-off in blood occurs when the semilunar valves are closed. All right. And so we're going to record this reading as our systolic pressure. Systolic pressure is the highest pressure in the aorta. Diastolic pressure is the lowest pressure in the aorta. And so we want to think about how those readings are recorded as our blood pressure. It's our highest reading over our lowest reading, systolic pressure over diastolic pressure, which can be captured at different points throughout the cardiac cycle, but they're only captured in this one vessel in the aorta, okay? As the majority of the circulatory supply leaves the ventricle and moves out towards the left side of the vasculature. Now in systole, the aortic valve is open, which makes sense as we are ejecting blood from the ventricle. And so now we're going to record the highest ventricular pressure. So during diastole, we got the lowest pressure, which is the drop-off after blood leaves the chamber. In systole, we record the highest pressure, which is at the very top before the blood completely leaves the chamber. And then we're also going to see that back swoosh or that back flow of blood against the closing valve. So that creates this sort of drop and then notch, which we refer to as the dichrotic notch in the aorta. Okay. We also want to describe the mean arterial pressure here. This is the average aortic pressure throughout the entire cardiac cycle. So important to think that this is just the aorta, not all of your vessels, but it can tell you a great deal about the driving force that moves blood throughout your entire vasculature. So the mean arterial pressure is the average pressure in the aorta. So when you think about the highest pressure being the systolic, lowest pressure being the diastolic, the mean arterial will be the average between those two differentials. And then it's going to be during the entire cardiac cycle, not throughout any one part, not throughout systole or diastole, but throughout the entire cycle collectively. And the reason the mean arterial pressure is so important is because it's the continuous blood flow through all phases of the cycle. And when we think about the valves closing, so example, when the aortic and pulmonary valves close, there still needs to be adequate pressure perfusing the systemic system to keep our organs receiving blood and oxygen, right? So even in times when the semilunar valves close, there still needs to be a mean arterial pressure that's maintained in the aorta that helps to move blood throughout so that our organs don't experience any interruption in that perfusion. So that is why the mean arterial pressure is so important. It's the average aortic pressure throughout the entire cycle. Now, when we look at the aorta specifically, we also want to think about the pressure reservoir that happens when the valves close. This is the ability of the aorta, because it's a large elastic artery, to store pressure in its walls during systole, which is the ejection phase, so that during the filling phase, when the semilunar valves close, or during diastole, you can use that stored or captured pressure to then propel blood throughout the aorta and throughout the circulatory system as well. So the aorta, being a large elastic artery, is very important in maintaining mean arterial pressure, okay, and keeping the pressure the same throughout the entire cardiac cycle. Okay, let's look at two examples of that. So here in systole, this is the ejection. The semilunar valves are open, which include the aortic valve. And then blood can leave the ventricle and out towards the systemic organs. However, because of the elastic nature of the artery, while blood is flowing, it's going to expand the elastic artery, and then we're going to be able to capture some of that pressure in the walls of the artery. Okay, so this is why we refer to the artery as a pressure reservoir. We can capture that pressure as we expand the artery, kind of like an elastic band, right? Or a rubber band. In diastole, now the aortic valve is closed. So this is what I mean by being able to maintain mean arterial pressure throughout the cardiac cycle, even in periods when the aortic valve is closed. So when this valve closes, our organs still need to maintain adequate perfusion. So now we can use the stored energy that has been captured in the wall, and we can release that via the elastic recoil, and that can maintain the same amount of flow towards our systemic organs, even during periods of ventricular diastole, when the valves are closed. All right. So this is why the elastic arteries are so important in that mean arterial pressure. Let's think about some of the ventricular volumes and how we can calculate them and what they can tell us about the health of the heart. So the end diastolic volume is the amount of blood filled into the ventricle at the end of diastole. So after the ventricle fills, what is the amount of blood that is sitting in that ventricle at the very end of diastole? And for the end systolic volume, this is the amount of blood that is in the ventricle at the end of systole. So after we have ejected blood from the ventricle, how much blood is remaining at the end of the ejection phase, or phase 3? Okay. So if we think about when we can detect these two readings, we can detect the end diastolic volume at the end of phase 1 or any time in phase 2. Because remember, the volume is the same in phase 2, the isovolumetric phase. Let's go back to this image here. So during phase 2, the volume is the same. Okay. If you look at the volumes here, at the end of phase 1 and throughout phase 2, we can detect the end diastolic volume. And then at the end of phase 3, or any time throughout phase 4, we can detect the end systolic volume, okay? So this is what's left back after we have ejected. So that is the time during the cardiac cycle when we can capture both of these readings respectively. Now, we can use these two readings to tell us other functions or other volumes. We can calculate the stroke volume. The stroke volume is how much blood was actually ejected. Because during ejection, we don't actually eject all of the blood from the ventricle. Some of that blood stays behind, which is the end systolic volume. So now we can calculate, based upon the total that was filled and the total that remains at the end of ejection, we can actually calculate the amount that was ejected during ventricular ejection or phase 3. All right. So our stroke volume is equal to our end diastolic volume minus our end systolic volume. And in terms of these actual numbers, our stroke volume is about 70 milliliters because our total EDV is usually 130 and our total ESV is usually 60. So if we subtract, that's usually about 70 mLs in terms of what was ejected. So notice that most of the blood is ejected. However, there's still a lot of volume that remains in the ventricle after ejection. Another fraction or another sort of volume that we can calculate based on those numbers is the ejection fraction. And this is the proportion or fraction of the end diastolic volume that was ejected. So if we had 70 mLs being ejected, based upon what we calculated as our stroke volume, and we divide that by our total volume filled, our end diastolic volume, now we can get a fraction. What proportion of the total volume filled was actually ejected? And so that's going to be about 0.54 or 54% ejection fraction at rest, which is to say about 54% of your blood actually leaves your chamber and about 46% of that will remain as your end systolic volume. Now, this is at rest, and this is going to go up during periods of exercise, during periods of exertion, and even in young folks and infants and children, athletes, we're going to see a higher number. Pregnant women may have a higher number. So this number can vary, but for someone at rest in a normal sort of stable or healthy state would be about 54%. Okay, and just to look at those numbers and how those volumes are calculated, end diastolic volume at being at the end of diastole, so at the end of phase 1 or any time in phase 2, and systolic volume at the end of systole, so end of phase 3 or any time in phase 4. And then from that, we can calculate the differential. So how much of that blood was actually ejected, which is our stroke volume. So this volume from 130 to 60, the change here is 70, which is our stroke volume. All right. And then the ejection fraction is the percentage of the stroke volume, a percentage of the end diastolic volume that the stroke volume happens to be, right? 70 divided by 130. Okay. Now we also want to think about the pressure volume curve. This is how pressure and volume are changing respectively with each other. So phase 1, this is the filling phase. So we're going to go from 60 milliliters to 130 milliliters as we fill about 70 milliliters during phase 1. And so we'll see that the volume is going to increase as the curve moves from left to right. However, the pressure is not going to increase very much. Very slight increase in pressure as we are filling into the chamber sort of passively. Phase 2, we're going to see that volume drops or increases. Volume will not increase, excuse me, remain constant, right? Because this is a linear phase in the loop here. This goes right up, indicating pressure rises rapidly, but volume stays the same at 130. And remember, this is the isovolumetric phase, so volume isn't moving. So this should be a linear phase as opposed to a horizontal phase in terms of the volume change. Phase 3, now we're seeing a drop off in volume. So we're going to see the volume is going to go up slightly. And then it's going, excuse me, volume is going to decrease. Pressure is going to go up slightly and then eventually drop off because this is the contraction phase of the ventricle. So notice that the volume goes from 130 back to 60. So we eject all of the blood that we filled at 70 milliliters during phase 3, hence the backwards curve creating this loop-like structure or this loop-like curve for the pressure volume graph. And then at the end here, phase 4, we see the pressure drop off steadily as we have isovolumetric relaxation, and the volume will remain the same at 60 milliliters. Okay, so this creates this pressure volume loop or curve that again can tell us a lot about the heart when it's in its healthy state, but also it can tell us about the heart in certain diseased states as well. So if we see changes to this curve where the curve becomes wider, that tells us that the heart may be having a regurg. One of the valves may not be working properly, and so the heart is not ejecting adequately, or there's some type of spilling of blood back into the atria or into the ventricle, which gives an inappropriate volume of blood remaining. So that's going to give us a larger curve. We can also see the curve move more to the right, which also tells us there's higher volumes, or the curve move more to the left, which tells us about inadequate volumes as well. That can be seen with heart failure and other types of heart diseases. Let's talk about the heart sounds. So let's kind of put all of that together and talk about how we get our two heart sounds because of the events occurring with the valves. So the heart sounds are created because of the turbulence of blood hitting against the closing valve. So when we hear that first heart sound, which is the soft pitched lub, that is the closure of the AV valves. And it's not the valves that are creating the sound, but it's the back shift of blood against the closing valve. So that creates an additional pressure, which kind of moves the blood or swooshes the blood back towards the valve, and that creates the sound. Okay. Now the second heart sound is a much louder sound, and it's a higher pitch, a dup. And that is the semilunar valves that are closing, so pulmonary and aortic valves closing. And that is because of a decrease in ventricular pressure. And then we're also going to see a back shift of blood in the arteries against the closing semilunar valves. So the heart sound is going to be a lub-dup, 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 so a softer pitch and a shorter dup, or lub, which is the AV valves, and then a higher pitch, slightly longer and louder dup, which is the semilunar valves. Okay, and this is going to be louder and longer because there's more pressure in the systemic vasculature. So when that blood hits against the back of the semilunar valves, it's a louder sound, and it's going to be for a longer duration, right? That lip dup, which is the heart sound.